In this video, we will learn how to use Laplace transform to solve a differential equation. Okay, now let's review what is a Laplace transform. Okay, for a given function small ft, its Laplace transform has been defined as 0 to infinity e to the negative st ft dt. Okay. For given s, you can calculate this improper integral. You find a number. Give another s, you find another number. So this, as a result of Laplace transform, give you a function of s. Okay. Now, if we know the capital Fs, we want to find small ft. That's the job for the inverse Laplace transform. Okay. So, if I know the capital F, I want to find the small st. Okay. Small ft. Then we just need to find the inverse Laplace transform. Okay. For example, Laplace transform, if ft equal to 1, it's a Laplace transform. We did that in a previous video. Its Laplace transform is 1 over s. Okay. So this, if I want to find the inverse Laplace transform of 1 over s, then that's equal to 1. Okay. Laplace transform and its inverse Laplace transform have such a nice property. Okay. Okay, suppose you know how to find the Laplace transform of f1t and f2t. Then we can find the Laplace transform for this whole function easily. What do you need to do? Just find the Laplace transform of f1t, then plus c2, which means a constant you can put out of the Laplace transform. You can put that constant out. That's because it's defined as an integral. So constant can be put out of that integral. Same for the inverse. Okay. So if you have two capital Fs, you just need to find its inverse one by one and put them together. This is very important properties. We use that all the times. F2S. Okay. Now, we're going to learn how to use this Laplace transform to solve initial value problem. Before we do that, we need some formulas. Okay. So, the first formula is we're going to learn is like this. We need to find the Laplace transform of f prime t. Okay. So, this one by definition is 0 to infinity e to the negative st f prime t dt. Now, let's use the integration by parts to integrate this. What is the integration by part formula? U dv equal to uv minus v du. Okay. So now first let's identify what is, we call this u, this is the dv. Okay. So our u here is equal to e to the negative st. Our dv here is equal to f prime t dt. Okay, then we need to find the du because we have du here. Okay. du equal to respect to t, okay, give you negative s e to the negative st. And the v here, you can find a v here by integrate it, so give you ft. Okay, u dv equal to v times u times v. U is e to the negative st times v, which is ft, minus v du. Du is a negative, so negative and negative give you positive. S e to the negative st, that's du, okay, they have a dt here, sorry. Du is you take a derivative with respect to t, then times the dt. So we'll integrate about the t, so s is a constant, you can put that out. Ft dt. So that's, this one is equal to, this is evaluated 0 and infinity, okay, 0 to infinity. Okay, so let t equal to infinity. Negative s is bigger than 0, so negative, when t go to infinity, e to the negative st go to 0, okay. So you got a 0 minus, replace t by 0. E to 0 give you 1, so you got a f0. Okay. Then we'll have the second term. The second term exactly is the Laplace transform, by definition, is the Laplace transform of ft. Okay, therefore, we got this formula. Laplace transform of f prime t, with the s here, sorry, is equal to s Laplace transform of ft itself without take a derivative, then minus f0. Okay, by using this formula, we can find this f double prime t, because this one can be viewed as f prime t, then prime. Okay, so let's use this formula. So only difference here is our ft, there is f prime t. So by using the formula above, we got s times Laplace transform of f prime t, then minus f prime 0. Okay. Then we use this formula again. They give us s times s Laplace transform of ft minus f0. This whole thing is then minus f prime 0. Okay. So let's put together. We can find the formula of this. The second derivative of ft, take a Laplace transform, give you s square Laplace transform of ft, then minus s f0 minus f prime 0. Okay. You can keep doing this. Okay. You can find the Laplace transform for f triple prime and so on and so forth. Okay, now we're ready to use the Laplace transform to solve a differential equation. Okay, now let's look at this example. Okay, it is long. Okay, so the equation we try to solve is like this: y double prime plus y equal to sine 2t, and y0 equal to 2, y prime 0 equal to 1. Okay, this equation is second order linear non-homogeneous equation. We know how to solve that before. Okay, here we are going to use Laplace transform to solve it. Okay, the first thing what we do is take Laplace transform of this on both sides. Okay, the left hand side is a function of t, so is the right hand side. So for given function of t, we can take the Laplace transform of it. Okay, those two functions are equal, so its Laplace transforms are equal to. Okay. And since Laplace transform is linear, so this gives you Laplace transform of y double prime plus Laplace transform of y. Okay, now in the book they have a table, okay, for the sine Laplace transform of sine 2x give you 2s squared plus 4. Okay, now we're going to use the formula we have before. Okay, Laplace transform of y double prime give you s squared Laplace transform of y minus s y0 minus y prime 0, then plus Laplace transform of y, okay, equal to 2 over s squared plus 4. Okay, now let's use capital Ys to denote the Laplace transform of small y's of t. So this equation can be rewritten as s squared capital Ys minus s y0. y0 here equal to 2. So you get minus 2s minus y prime 0, which is 1. Then plus another capital Ys equal to 2s squared plus 4. Okay, now let's simplify this. We have two terms with capital Ys. Okay, so you got s squared plus 1. That's coefficient of Ys. And put the other things on, known things on the other side. Okay, s squared plus 4 plus 2s plus 1. Okay, once you try to get a common denominator, you got s squared plus 4 and 2s to the third power plus s squared plus 8s plus 6. Okay, so we can solve for capital S. Is equal to, you divide the s squared on both, s squared plus 1 on both sides, s squared plus 4. So we got a 2s to the third plus s squared plus 8s plus 6. Okay, we find the capital Ys. That's not what we want to find. We want to find the small y's of t. So to find the small y's of t, is our solution is equal to inverse Laplace transform of capital Ys. Okay. So we just need to find the inverse Laplace transform of capital Ys. Okay, in the book there's a table. You can look at the Laplace transform and try to find it. Try to find the small, its inverse. Okay. So this one is hard to do. Okay. First, we need to rewrite this things. 2s squared to the third plus s squared plus 8s plus 6 divided by s squared plus 1. S squared plus 4. First, we need to use a partial fraction, okay, to simplify this expression. Okay. So, partial fraction can be written as two things add together. Okay. This simplified whole thing. So, the denominator is second order polynomial. So, the numerator, the right form should be as plus b. Same thing here. Second order should be CS plus D. Okay. So we want to find A, B, C, D such that the left hand side equal to right hand side. Okay. So what we need to do, just add them together again. So you got S squared plus 1, S squared plus 4. Okay. So you got AS plus B times S squared plus 4 plus CS plus D and S squared plus 1. Okay. So we want to choose A, B, C, D such that the left hand side equal to right hand side. Okay. They have the same denominator. What do we need to do? Just compare the numerator. So we got a 2s squared, 2s to the third plus s squared plus 8s plus 6. We want to equal to the numerator on the right hand side. Let's simplify this. Okay, so s squared times as, you got as to the third, then plus bs squared, then plus 4as, then plus 4b, okay. Then plus cs to the third plus ds squared plus cs plus d. Okay. Now let's simplify the right hand side. Put all the term with s to the third power together. So you got a plus c, s to the third, plus s squared term is b plus d. That's the coefficient for s squared. Okay. The term with s there is 4a plus d, plus c, s. And the constant term is 4b plus d. 4b plus d. Okay, that's constant term. So you compare corresponding coefficient. So the coefficient for s to the third is a plus c, that must equal to 2. The coefficient for s squared, b plus d, must equal to 1. Then 4a plus c must equal to 8. The constant term 4b plus d must equal to 6. Okay. So we got a 4 equation and 4 unknowns. I'm not going to solve that here. Okay. So if you solve that, you are going to find a here is 2, b is 5/3, c is 0, and the d here is -2/3. Okay, so what that means? That means capital YS can be written as s squared plus 1, and the numerator is as, is as plus b. A is 2, 2s plus 5/3. Then plus s squared plus 4. C here is 0, so plus d, so minus 2/3. Okay. So to find small y's of t, we need to find the inverse Laplace transform of capital YS, which can be find inverse Laplace transform of 2s plus 5/3 s squared plus 1, subtract inverse Laplace transform of 2/3 s squared plus 4. Okay. See, that's important. Okay, if we don't do this partial fraction, it's just impossible to find the inverse Laplace transform for this one. Okay, now, so what we need to do now is to find those two inverse Laplace transform. Okay, now let's do that. Okay, so the inverse Laplace transform of 2s plus 5 over 3 over s squared plus 1. We use this property, give you 2s s squared plus 1, then plus inverse 5 over 3 s squared plus 1. Okay, this 2 you can put that out. Okay, so put a 2. You got s over s squared plus 1. Then this 5 over 3 can be put that out too. So give you 1 over s squared plus 1. And it gives you, if you look at the book, in that table they give you 2 cosine t plus 5 over 3 sine t. Okay, we're almost there. Okay. Now let's find the next one. Okay. Next one is we want to find an inverse Laplace transform of 2 over 3 s squared plus 4. That's okay. That's equal to 1/3 inverse Laplace transform 2 s squared plus 4, which give you 1/3 sine 2t. Okay. So we put everything together, we find small y sub t, which is the Laplace transform of capital Ys. We find all of those put together give you 2 cosine t plus 5 over 3 sine t minus 1/3 sine 2t. Okay. So finally we're done. Okay, so how do we use Laplace transform to solve a differential equation? First thing we need to do, take Laplace transform on both sides and use a property of it. So we can easily find the capital Ys. The hard thing is find the inverse. Okay. All right.